know what the area of a rectangle is?
Well, if you've got a rectangle, say, of width A and height B, what should the area of this rectangle be? Well, the area of this rectangle is A times B.
So what's the area of a triangle?
Well, if we've got a triangle, say, of height B and width A, right, the area of this triangle is 1/2 AB.
But why? Why is that the area of a triangle?
Well, this is really what the area of the triangle has to be in order to be consistent with the area of the whole rectangle. I mean, look, I could take two of these triangles, right? Here's two triangles, both have width A and height B, but if I push those two triangles together, then I've got the A by B rectangle. So the area of these two triangles together has to be the area of the rectangle, A times B, but each of these triangles has half the area of the rectangle, so the area of just the triangle should be half the area of the rectangle. Another way to say this is just that, areas sort of add. I mean, area of some figure plus area of some other figure is equal to the area of those two things together, right? In this particular case, the area of this triangle plus the area of this triangle is the area of these two things together, which is the area of a rectangle.
You can play this kind of game to relate the areas of different figures that supposedly have the same area.
For example, I could start with a rectangle of width 2 and height 1, or I could start with a square whose side length is the square root of 2. Now, both of these figures have the same area, right? The area in both of these figures is 2. And you might ask, well, if the whole deal with areas is just that they sort of cut up and add appropriately, is it possible for me to cut up this figure in order to get this figure? And yeah, it is in fact possible, right? If I cut along the diagonals here, these four pieces can be rearranged into these four pieces here. So I mean, very visibly, right? If you believe that, sort of areas add in this way, that I'm allowed to rearrange pieces, then you might believe that these two things have the same area, regardless of whether you do the calculation or not, right? These two pieces have the same area because I can take this thing and cut it up and get this thing.
Well, here's a challenge for you right along these lines.
For instance, can you take a 3 by 1 rectangle and a square of side length root 3 and visibly show that these things have the same area? I mean, yes, the calculation, right, is telling me that they both have the same area of 3. 1 times 3 is the same as the square root of 3 times the square root of 3. But what I'm looking for is some sort of geometric proof where you cut up this thing and rearrange those pieces to build this thing, right? That's your challenge.
So this is really fascinating, right? What is area? Area is a number, but that number captures this geometric idea that if two things have the same number, the same area, then you can take the one thing and chop it up into pieces to get the other thing. And yet that perspective is totally destroyed as soon as we start thinking about something with a curved boundary, like a circle.
So here's a unit circle, by which I mean that the radius has length 1 unit. And the area of this unit circle is pi square units.
I mean, yes, we know what the formula for the area of a circle says, right? It says that the area of that unit circle is pi square units. But what does that mean? What does it mean to say that the circle's area is pi square units? Well, I'll tell you what it doesn't mean.
It doesn't mean that I can start with a rectangle of area pi square units. So say a rectangle of height 1 and width pi, right? To say that the area of this circle is equal to pi does not mean that if I just start with a rectangle with that same area, that I can necessarily make some finite number of cuts to this rectangle and take those pieces and rearrange them to form this disk. right? There's really two competing concepts here. You've already got an idea of area, because you've seen area before. And this idea of area is really based on this idea that two things have the same area if you can cut the one thing up and rearrange the pieces to make the other thing. But as soon as you're dealing with objects with curved boundaries, say, you've suddenly got a problem, because it's not going to be possible for you to take this object and just chop it up and produce this nice smoothly curved object. So somehow you've got to refine what area even means. When I say that the area of a circle is pi square units, I'm secretly speaking in the language of limits. So when I say that this circle has area pi, I mean that if I, say, cut it up into small enough little rectangles, the area of these rectangles, which actually makes sense because I know how to calculate the areas of rectangles by multiplying their widths times their heights. So if I add up the areas of these rectangles, I'll get an answer that's as close as I'd like to the number pi. And I can get the answer as close as I want, provided I make these rectangles thin enough. And it's only in that sense that it even means anything to say that the area of the circle is pi. It's in the sense of that limit. So even defining area requires talking about limits, which I think is remarkable. I mean, we learn about area in elementary school, right? We never talk about limits in elementary school. And yet somehow there's a real depth, a real subtlety to even this concept of area, And I think that's really exciting, right? It suggests that there's something interesting yet to be learned, even about concepts that we think we understand really well.